Welcome to Module 5, the final group of lessons in this course. We've come a long way since first learning about binary and other number bases, then logic, then sets and functions, and then counting. In this last module, we'll focus in on perhaps the biggest concept of the whole course, recursion. We've seen this idea before, particularly with the binomial coefficient, and in this module, we're going to drill deeply into this idea and learn how to work with recursion and how to craft mathematically sound arguments about recursion. But first, let's start small. Here's an interesting visual pattern that I'd like you to think about. It's a sequence of figures, and the first figure is just a circle. The second is this triangle, and the third is this triangle, and here's the fourth. Pause the video now and see if you can guess the pattern and draw the next figure in the list. So here's the next one that I had in mind. What's the pattern? It looks like in order to create a new figure, we look back at the previous figure and add a row of dots along the right side of the triangle. So the fifth figure should look like this. Now let's count the number of circles in each figure. The first one has 1, the second 3, then 6, then 10, then 15. Can you guess the next one? Can you guess it without drawing a triangle? Try it. Did you guess 21? Well, let's draw the triangle and see. The visual pattern says we make the new triangle by taking the previous one and adding a row of circles on the right. We already know that the previous figure has 15 circles in it, and since the previous right side had 5 circles, the new one should have 6. So we just need to add the 6 circles here, and that gives us 21 total. This list of numbers is called a sequence. This word sequence refers to any ordered list of numbers. The numbers in a sequence are called the terms of a sequence. So a sequence is not a set of things, it's a list with a definite first term, second term, and so on. Sequences occur throughout mathematics and computer science in all kinds of ways, and they are often a key to many applications as well as interesting objects unto themselves. We often label the terms of a sequence using a letter with a subscript. For example, to denote this sequence, 1, 3, 6, 10, 15, 21, and so forth, we could use the letter T for triangle with subscripts to tell us which term in the list we mean. So T1 is 1, T2 is 3, T3 is 6, and so on. A number in the subscript is called an index, and the plural form of index is indices. This particular sequence happens to have a special name. It's called the triangular numbers because the numbers come from this visual pattern we see here. Here's another sequence, which this time the index starts at 0. F0 is 1, F1 is also 1, F2 is 2, F3 is 3, F4 is 5, F5 is 8, and so on. So first of all, note that unlike with sets, sequences can and often do have duplicate terms. The pattern in this sequence is that the first 2 terms are both 1, but every other term is the sum of the previous 2. This one is called the Fibonacci sequence, and it plays a very big role in math and computer science. Sequences can also be spelled out with a formula, like this. Look at the sequence G, where gi is equal to 2 to the I power for each I in the natural numbers. So G0 is 1, G1 is 2, G2 is 4, G3 is 8, and so on. But sequences don't have to have any particular pattern at all. Look at the sequence H given by H0 is 3, H1 is 1, H2 is 4, H3 is also 1, H4 is 5, H5 is 9, and so on. The pattern here, if you can call it that, is that Hn is the nth digit of the number pi. There's no real formula or visual pattern here. It's just a direct mapping from the index to the digit. As we just saw, there are 2 main ways to generate sequences. One is with a closed formula, where you just plug in the index to the formula, and the formula tells you what the sequence term is at that index. For example, that sequence where gi is equal to 2 to the ith power uses a closed formula, and we can quickly generate as many terms in this sequence as we want using Python or a spreadsheet. Here's another. Bn is the sequence whose nth term is 3 times 1.1 to the nth power. And here are the first 10 terms of that sequence. This shows you that sequences don't have to consist only of integers. However, the indices of a sequence do have to be integers because they are counting the positions of the terms. The other major way to generate a sequence gets us to the heart of this module. We can define sequences recursively. A recursive definition of a sequence computes a term of the sequence using one or more of the previous terms in the sequence. The Fibonacci sequence was recursive because the third, fourth, and so on terms of the sequence were the sum of the previous two. We can phrase this using notation by writing fn equals fn minus 1 plus fn minus 2. That relationship is called a recurrence relation. A recurrence relation is a math expression that tells how one term in the sequence relates to previous terms. We also had some starting terms given as part of the definition of the sequence, and those are called the initial conditions. A complete recursive definition of a sequence requires both a recurrence relation and initial conditions. With both the recurrence relation and the initial conditions in place, we can compute any term of the sequence we wanted. For example, if I wanted to know what f3 is in the Fibonacci numbers, then the recurrence relation says it's equal to f2 plus f1. But what's f2? Well, that's f1 plus f0. If I only had the recurrence relation and no initial conditions, this would just keep pushing me further and further backwards. In order to actually find the terms in the sequence, I need initial conditions. In the Fibonacci numbers, those initial conditions are f0 is 1 and f1 is 1. With those initial conditions and the recurrence relation, I can compute this term and any others I wanted. As another example, look at an equals 2 times an minus 1, a recurrence relation with initial condition a0 equals 3. Let's write out the first 5 terms of this sequence. Well, the first one, a0, is given to you. That's equal to 3. a1, by the recurrence relation, is equal to 2 times a0, so that's 6. Likewise, a2 is 2 times a1, and that's 12. Pause the video and see if you can get a3 and a4. So a3 is 2 times a2, which is 2 times 12, or 24. And a4 is 2 times a3, which is 2 times 24, which is 48. So those are your first 5 terms, 3, 6, 12, 24, and 48. Notice we're just doubling the term each time, and that makes sense when you look at the recurrence relation. Notice with this sequence, we needed only one initial condition because we only had to go back one step in the sequence to compute a new term. Whereas with the Fibonacci numbers, we had to go back 2 steps, so we needed 2 initial conditions. Many times we can represent a recursive sequence with a closed formula and vice versa. It's going to be important to phrase a given sequence in both ways if possible. Let's try this with the triangular numbers we opened with. Can we come up with a recursive definition for this sequence? It helps to go back to the visual pattern. The first number was 1. The second one we got by adding 2 circles onto a triangle. The third one we got by taking the second figure and adding 3 circles onto the triangle. The fourth one we got by taking the third and adding 4 circles. I think I'm beginning to understand the pattern here. At stage n, I get tn by dropping back to the previous stage, n minus 1, and adding n circles. So tn should be tn minus 1 plus n. That seems to be the right recurrence relation, but I still need the initial condition, but that's t1 equals 1. So here's a recursive Python function that should generate this sequence if I'm right. You can see in the second line I have the initial condition coded in, and then in the remaining lines it uses a recursive function call to implement the recurrence relation. Down below, I'm going to make a list comprehension using this function to generate terms of the sequence. And when I execute it, I can see that it seems to be generating the right numbers. So I think my recursive definition, both the recurrence relation and the initial condition, was right. What about a closed formula for this? Well, this is harder here. Just looking at the numbers, it's hard to guess. There's not a totally obvious formula that produces all of these. But remember the problem-solving concept of looking at the problem in different ways. If I look back at the picture and draw the triangle more like this, I can make a copy of that triangle and rotate it and attach it to the original triangle to form a rectangle like this. This rectangle has n circles on one side and n plus 1 on the other. The total number of circles in the rectangle is therefore n times n plus 1, but the original triangle has exactly half of those circles in it, which is n times n plus 1 over 2. So that's a closed formula. Is it right? Well, here's a list comprehension that tests this directly. And when I do that, I can see that it does seem to produce the same sequence. So note there's no need for initial conditions with a closed formula. The formula just directly produces the output. And so here we've calculated the triangular numbers both with a recursive definition and with a closed formula. In this video, you learned what a sequence is, how to represent one recursively using a recurrence relation and initial conditions, and how to represent one as a closed formula. And we've gotten a taste of how to look at a visual pattern and write a recursive definition for it, also how to use the same visual pattern to write a closed formula. Next up, we're going to discuss how to add and multiply terms of a sequence together using a notational trick.